All right, maybe. Okay, let's begin. Uh, Welcome. My name is Chung Eng Seong, and I'm taking part two of this course, and I will do the lectures from this week until week 13. So I've distributed the slides. I'll first go through these slides, which is the introduction information that you all will need. All right. Yeah, how will we conduct the course? Basically, you will watch the videos, and in these 2 hours, we'll go through highlights. So the videos are already in YouTube, and I'm going to give you the study schedule for it. So in YouTube, now I know that if you watch YouTube, there's a lot of advertisement. So if you are not happy with the advertisement, you can use ad blockers, or you can just download YouTube using this YouTube-DL YouTube downloader. Now, MATLAB, I'm going to ask you to use MATLAB only as a calculator so that you can verify your results. Okay, so if you do not need that, you don't need to learn MATLAB, but do learn MATLAB because it's very useful. This is the schedule of the course. Basically, we're only from week 8 to week 13, and I number my chapters as chapter 6, 7, 8A, and 8, and 9. So notice that the order is a little bit different. That's for historical reason. Please follow this order. Uh, I call chapter 6 orthogonality and orthogonal projection. Chapter 7 is least squares. Chapter 8A is complex numbers. So this is new. In the past, complex numbers was in another course, but that course was taken down. So complex numbers now is being introduced within linear algebra, which is okay because actually complex numbers can be in matrices, and you will see that in action in 8A.3, which is the DFT. Uh, and in week 12, we'll do eigenvectors and eigenvalues, and that will take 3 hours. So this is the hours of that I have recorded. Most students tells me that they can play me at 1.5 times speed. So there you go. You will watch me in less hours than this. Tutorial schedule. In this week, if your tutors have already finished part one, then there's no tutorials for you. But if not, then they can use this week to finish part one, as in week 1 to 7. And for tutorial 6, we will begin from next week. So we'll do it in very fast pace. This is the pace that we're going to do it in. All right. Now, many of you will be interested in this. We'll introduce SVD as chapter 9. But I guess you say that since this is not in the exams, you guys are not so keen, but it is recorded anyway, or the slides have been given. The quiz will be given on week 13 on Monday. And if we need to do some requiz, we'll do it on Friday or whatever schedule that we need to do the requiz in. Right. Now, where's the YouTube recording? So if you paste this link, you will see this. So this is my YouTube link. It has existed for almost 4 years now. It was recorded during COVID, and yeah, it survived until now. So that's nice. So it is organized in this way. Part one, I actually recorded tutorial 3, 4, 5, 6. It used to be called tutorial 1, 2, 3, 4. I mean, so, but never mind. It's now called tutorial 3, 4, 5, 6. If you have problems figuring out, then you see tutorial 3 is linear equations, tutorial 4 is matrix algebra, so on and so forth. So this is the tutorial. But you still need to go to tutorial now because we take attendance, right? So, but if you have any problems, you can watch these tutorials for all the questions. Part 2 lecture playlist. Now, this is what you need to watch by yourself, given the schedule. So you have chapter 6, chapter 7, chapter 8A, and chapter 8. So this is the order you're watching it in. All right. Again, I would suggest you download the videos and then watch it at your own leisure. And I've recorded tutorial 6, tutorial 7, tutorial 8. so I will find time to record tutorial 8A one day. Now, I have watched a lot of videos online, and so these are some of them that I recommend to you that is of the same standard as ours. You have Three Blue One Brown, you have this guy in King's College London, you have MIT here, and you have this Hebrew University, Tel Aviv. Okay, so you can watch any of these, and it will give you a very good representation of what we expect you to know. Right, so this is the recordings. Finally, yeah, quiz 2. So in quiz 2, we're going to do the lectures. During the lecture hour, we are going to give you the lockdown browser again and do the MCQ for the quiz. Some of you all asked me when would the quiz results be released. I do not know. You have to ask Professor Tipu for that. And yeah. Okay. For the quiz question, you'll notice that I have given this coverage 6, 7, 8A, and 8 of part of chapter 8. Now, if you're absent, that means you have more time to study because there's a Monday, and then all the chapter 8, all sections will be covered, and it will be harder because you have more time. So again, absentees, if you're absent for whatever reason, you must have an MC to take the requiz. But because you have absent yourself and you have more time to study, then the requiz would definitely be more difficult and have more coverage because you have more time to study. All right. Now, if you need to contact me, please use your NTU email to send and tell me who you are, what class, and because I teach 2 class courses, you have to tell me which course you're talking about, and this is linear algebra. And for tutorial matters, please approach your tutor first. And for MCs, for quizzes, you must send an MC, and I will do a requiz for you. Or if there's any problem with the lockdown browser during the quiz. Okay, so that's what I have first, and then yeah, we can do the lecture proper. Now, because I cannot see any of y'all and I do not know what's happening, uh, can someone again type on the chat box to tell me that whatever I've said is okay? All right, cool. And now you're watching my black screen, I guess. Yes? Okay, great. I should try to let your chat with me, right? Why can I see the chat? Yeah, I can see the chat. Okay, great. Now, as promised, I'm going to overview this course. Now, I've injured my hand, so my writing is hopeless, but I will try. Okay, so I'm going to start with chapter 6, orthogonality. Okay, cool. And we'll begin by remembering what we are talking about. And we are in this vector space Rn. And if you remember what is vector space, it is actually this thing. And you think that this is a vector, okay? You know, this is a column vector with n elements in it. And in these n elements, we write it in this way, and we give a bar to say such that this is a set of vectors such that xj, each of these element, where j equals to 1 to n, belongs to, and if I say that it belongs to real, means all these elements here are real numbers. If I put C, means all these elements are complex numbers. And then we're done. So in fact, Rn is nothing but a set of vectors, and these vectors can be any of these vectors here in the whole space. The other way to draw this is, of course, we draw a box like this, and this is a set, and we have all these elements here. And for example, each of these elements looks like, for example, 1, 2, and minus 1, for example, belongs to R3 as an example. And this guy belongs to another vector, maybe 2, minus 1, minus 1. And then, of course, now we can say this vector here and this vector here can be added together. So we have an operation of add, And then we'll give you another new vector. And then this vector is, of course, the addition of these two vectors, which is 1, 2, and minus 1, plus 2, minus 1, minus 1, and give you a new vector. That's it. So whenever you're in vector space, please remember we are talking about a set, and we can add, and we can scalar multiply. So we can use a number here, and this number belongs to the real, and we are saying that these two operations that we deal with, these elements in this vector space, will stay in the vector space in this set. So this is the abstract idea of a vector space. And with that, with that introduction, we can do a lot with it. We can do linear combinations because we are scalar multiplying a vector, and we are adding vectors up. Okay, but what else can we, or what else do we want to to do with vector space? One, norm. So we want to introduce the concept of the norm of a vector. So X belongs to some vector space. So maybe we concretely say R3, for example. All right. And then we give you a simple example of X. Oh, well, I use V. So let's use V then. So V is equals to 1 and minus 1 and 2. So V belongs to R3. And what does the notation nor this two line V means? The language is the not very official language, but at least what we say is the length of, or we should say the norm of. So norm is the technical term. Length is the the language we use in the street. Okay, the length of a vector. So what does the length of a vector means? Then of course, if we are in the Euclidean world, which we are, then we'll use the Pythagoras theorem. And then we realize that in Pythagoras theorem, if you have A and B, and this is a right angle and this is D, then C is equals to square root of A squared plus B squared. And we continue to use this idea of the Pythagoras theorem for length. Length is the length of this hypotenuse. So we also put these 3 points in some space, and then we want to measure the length from the origin to this point vector space. So technically what we are really doing is that we are putting it in a 3-dimensional world. So we go 1 along the first axis. So let's call the first axis, let's say first axis is X and Y and Z. So this is X, Y, and Z. So we go along 1 unit along the first axis, minus 1 unit along the second axis, which is here, and then 2 units up, which is here. So the vector is somewhere here. So this is 1 along first axis, minus 1 along second axis, and 2. And then the norm of V is basically this length over here that we are interested in. And then this length is measured with respect to the origin, and you can see right angle triangle here. So we can actually use the same idea of the Pythagoras theorem, but now in 3 dimensions, which is square root of x squared plus y squared plus z squared. And of course, in this very simple example, we do 1 square plus minus 1 square plus 2 square. And then, of course, we get 1 plus 1 plus 4, we get square root of 6. So we know how to do norm now in R3. And of course, if you are in Rn, then so how to do norm in Rn? Norm in Rn. It is nothing but, let's say, V belongs to, oops, V, oh dear. All right, V is equals to square root of, now, how do we do this? V1 square plus V2 square plus Vn square. And V is equals to V1, V2, Vn. So you know how to do norm in R3, you know how to do norm in Rn. And we write this equation. Actually, this equation is very, very tedious to write. We never write norm like this. Okay? So instead, what do you think we do? Okay, so this is the first way we write norm. The second way we write norm is, guess guys, V transpose V. So what is V transpose V? V transpose V is a row vector, V1, V2, Vn, V1, V2, Vn. So this is a 1 by n. This is a n by 1. Therefore, we get 1 by n by 1. We get 1 by 1. And therefore, we get a scalar as we wanted. So a row vector multiplied by a column vector is a nicer way. And in fact, we write it in this compact notation, V transpose V, to get the norm. But did I forget something? Yes. Where's the square root? So we need the square root. So it's V transpose V, square root. And then you'll realize that there comes a lot of time when you write it this way, square equals to V transpose V. So don't forget. So if you square this, then the square goes to the left side. Therefore, you get norm square equals to V transpose V. So sometimes you'll see the notations like this as well. All right. What else? Is there a compact way to write this guy? Yes. Okay, so now let me write the compact way. Summation I equals to 1 to n Vi square. So instead of writing it as, this sum, we use the sum operation and write it more compactly. Okay, you just need to know all these ways to write norm. And so now, what have changed from 10 minutes ago? Before, you only were in the vector space and you know how to add vectors and you know how to scale and multiply. After this 10 minutes, you realize, okay, I now can measure the length of a vector. What else do we want to share with you? Well, so when we talk about length of vector, it must have some property. Okay, so theorem 3.2.1, which is at page 3 of 6.1.2. Let's open it up. Right. So the first thing you must remember is that anytime you see the word a norm of a vector, it's a positive number. It can be 0, but it will never be a negative number because we are talking about a length here. So anytime when we declare something to be a norm operation, it must eat up a vector, B, and it must spit out a number, scalar, that is non-zero. Non-negative. And it can only be 0 if the vector that is being sent into this operation is a 0 vector. And the other important one is that you observe this homogeneity where the k is a constant and we can multiply by k and this k can bring out. So it becomes an absolute value. So k can be a negative number inside, but once we multiply, once we bring it out, it will become an absolute value, positive value, because we don't have a negative norm. Okay, and the proof is here. All right. So we are done with norm, and now because we're going to do something slightly more exciting now, which is how to relate angle between two vectors. And we introduce the dot product. So the dot product takes in two vectors. So for example, A and B are two vectors, and A and B belongs to, let's say, Rn. And then how do I express the dot product between two vectors is A. So this is the way we typically introduce the dot product. We say A dot B. There's another way that we can also write here A comma B with this anchor bracket. So this is called the dot product. This is called the inner product. Dot product is the special case of the inner product, the most special case that deals with, I guess, the real vectors. So this is dealing with real Rn. And inner product generalizes different vectors to Cn or whatever, even A as a function. Okay, generalizes the dot product. All right, let's see. So let's introduce what the dot product does when we have these two vectors. Okay. Again, we have A and B belongs to Rn, real. So we define. Okay, this is a definition. So you just have to remember definition. Definition is something we give to you, and you have to use it. So when we say A dot B, we are saying that we are taking the norm of A, the norm of B, cosine theta. Oh, okay. So what is this? This is the angle between the two vectors. Which two? A and B. So now, with this dot product, we are given a new way, a new tool, or a new, what do you call it, mechanism, such that we can measure not the distance between A and B, okay? It is the angle between A and B. So, so suddenly we are given a new toy, right? And this is one way you can you can calculate A dot B. Now, I'm going to show you three different ways to calculate A dot B. Okay, so this is the first way. The second way, A dot B also can be calculated as A1 B1 plus A2 B2 plus dot 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 AN BN if we are in the Rn space. So it's saying that take the first element of A. So again, when I say A1, it is the first element of A. B1, first element of B. So if you really want to be pedantic, then I say A equals to A1, A2, dot, 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 AN. So similarly, B also same, okay? So now you recognize what is A1, all right? And then B1, B, of course, it will be the same. B1, B2, dot, 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 BN. All of them belongs to Rn. So this is the second way. You realize that, hey, I now have two ways to calculate. If I'm given vectors A and B, this is the easiest way to calculate the angle between. If I'm only given the norm and the angle, then this is another way. Okay, so, and then of course, we don't like to write it in this way. Again, we like to write it as A transpose B. Why A transpose B? Because this is simply the vector A as row vector multiplying by the column vector. So you realize that, hey, isn't this very similar to what I've shown you in the previous slide, like this guy? So you realize that norm has a very close relationship with dot product, because norm is just saying this same V with this same V. While the dot product is generalizing, we can use A related to B. Of course, if you do A related to A, then you are basically creating norm squared. All right, now let's have some examples. So the easiest example I would show you is this. This guy is 2, 2, is A. B is 1, 0. And A and B belongs to R2. And now we want to find A dot B. That's all. So it's very simple. Among the ways that I would play with, the easiest one would be the second way, which is A dot B is equals to A1 B1 plus A2 B2. And then, of course, we multiply the first element, 2 by 1. So 2 times 1 plus 2 times 0, and the answer is 2. Finish. The length, the A dot B gives you 2. But then you say, hey, where's the angle, right? Where's the angle? You're only giving me A dot B. You're not giving me the angle. Where's the angle? Angle is here, theta. The angle between the vectors of these two vectors. And of course, immediately it's obvious to you how to calculate the angle. How do you calculate the angle? Opposite over adjacent. So tangent theta equals to 2 divided by 2. Theta equals to arctangent of 1. And this is pi over, is it pi over 4? Yes. All right. So now we can calculate it visually because we're in R2 space. Now, how to calculate it using the dot product? Well, remember the first equation gives us A dot B, and now we get 2, right? Is equals to 2 is equals to norm of A, norm of B, cosine theta. Therefore, cosine theta equals to A dot B divided by norm of A, norm of B. Now, A dot B is 2. Norm of A. What is norm of A? Norm of A is 2 square plus 2 square square root. So it's square root of 2 square plus 2 square. What about norm of B? Norm of B is 1 square plus 0 square. So it's square root of 1 square plus 0 square. So the answer is 2 over square root of 4 plus 4 is 8, right? And if you work it out, then theta equals to A cosine this whole thing. And the answer will be pi over 4. All right, now I'll show you in MATLAB. Okay, so never trust your own calculation because it could be wrong, right? And let's try with MATLAB. So MATLAB to me is a calculator that does very fancy things, and I'll show you how I'll do it. And A equals to, so what is A? 2, 2. And I put the dash there to make it as a column vector. and B is equals to 1, 0. So, what I'm going to do is I'm going to plug in this equation. A cosine something. Okay, let's try. Let's see. A cos A dot B. A transpose B divided by norm of A times norm of B. And this is it? What value is this? Times 180 divided by pi, 45 degrees. Pi divided by 4, 0.7854. So I got it right. Okay. So guys, I mean, when we use MATLAB, we're actually using it as a very powerful calculator that understand a lot of these vector matrix notations, norm, and even the word pi, right? Okay, I'll pause here for a while. Can you all raise up your hand to tell me if you understand or if you all have any questions so far? Yes? Okay. Can you all type something on the chat board to let me know that I've not been mumbling to myself, please? Okay, great. Okay. So you realize that, hey, to me, if you look back, right, we're going very fast, right? We went from vector space, right? We see vectors as elements and we can plus and multiply by scalar. We have calculated norm and we now understand how to find a length of a vector. And with a length of a vector, we now introduce the dot product, which we deal with two elements, and then we can find the angle between the two vectors. And you realize that, hey, there are multiple ways we can find the dot product between two vectors. Okay, so we are going at this speed. And now, what must we understand? We give you a nice simple example and we show you how to do it in MATLAB. Okay, now, dot product is a special example, maybe, instance of the inner product. So I show you this notation. I want to play with two vectors, A and B. So I need two vectors here. I need to introduce a notation to tell you I'm playing with these two vectors. So the dot product use this notation. The notation by the inner product is this, A comma B, and this is the notation used. Now, both of these are families of, I mean, they are inner products, so they must possess four properties. Okay? So we leave it abstractly to say, I mean, A dot B, we have defined what it looks like. But you know that arrow A comma B, right? We haven't tell you a single thing. But for it to be called an inner product, it must satisfy four properties. So where is these four properties? It is at 6.1.3. Now let me open up the slide. And it is in page 7. And to be called a valid inner product or dot product, it must satisfy these four properties. And you realize that the dot product we have defined will satisfy all these four. And therefore, it is a valid dot product, or we should say it's a valid inner product. So remember, dot product is to give you the angle between two vectors. Therefore, u dot v should be the same as v dot u. Otherwise, what are we comparing? So it's symmetric. Okay? And then distributive here basically means that u dotting with this sum is the same as u individually operating on each of them plus this guy. So distributive with the dot product. K is a constant, so K can bring inside homogeneity. So we can dot product first and then multiply by K, or we can K multiply by U and then dot product with V. And the dot product of itself, so this we realize is a norm, okay? The norm square. V dot V is actually the norm square, the length square, and it can only be zero if we are having the zero vector. So this was what I was saying. V dot V. Hey, doesn't this look like the norm square? And yes, it is. It's exactly the norm square. So actually, once we have given you a dot product, then you get a norm for free. That's what we are saying. Okay. All right. So that is the dot product. And the last thing which I want to tell you in the last couple of minutes is this. Inequality. Some important one. The two important one, Cauchy Schwarz and the which inequality? Oh, triangle. So we are going to only introduce these two inequality. Our course is an engineering course. We are going to use this inequality. We're not going to be proving it as much as the other math student. So let's begin with Cauchy-Schwarz. U and V belongs to Rn. So again, actually this inequality can be generalized to very esoteric vectors, not even Rn, but we're going to be sticking to Rn in our description here. So u dot v, what is u dot v? Is a dot product between two vectors. The dot product between two vectors will return, can be positive numbers, can be even negative numbers, okay? So u dot v is just a scalar, but can be positive or negative. Let's take the absolute value of it. So now it's all positive values. And Cauchy-Schwarz says that this value, the dot product between these two guys, will always be less or equals to the norm of u multiplied by the norm of v. So this is a very interesting and very special relationship. What has the length of each of these individual vector got to do with dotting between two vectors, right? That's what we are trying to say. And he says that there is this inequality. There's no way this guy will be larger than the multiplication of these two norms. You can only get as far as equality. This guy is equals to this, and under a certain situation. Okay? So what is so special about it? It provides upper bound. U dot V, the absolute value of U dot B is bounded by these two guys. Bounded, upper bounded by the norm of U, norm of V. So whenever you take two dot product and you take the absolute value of it, you will never be larger than the individual of the norm multiplied by the other guy. Okay, so this is one useful thing. And the other thing is they are equal only when the direction of U and V is dependent, is the same. The same basically means that if I have if I have U pointing here, and then I have V pointing to the same direction. Okay? Now, pointing to the opposite direction is also the same direction. Can opposite direction is negative 1 times the original direction. So in here, when we talk about the same direction, we include opposite direction. So please be careful here. Okay, so what are we talking about? All right, let's play with this. Let's have U here, and we have V here. This is U plus V. Sorry. Wait a minute. Let's have an example. Let's have an example of this guy. When are they equal and when are they less than? Equal is the easiest to show you. So U is, let's say, 1, 0. V is minus 2, 0. So what is U dot V? It is 1 times minus 2. So it is 1 times minus 2 plus 0 times 0, which is 0, absolute. Then I get 2. So U dot V absolute is 2. Norm of U is 1, because this is only 1 square plus 0 square square root 1. This guy is norm of V equals to minus 2 square is 4. 4 plus 0 square is still 4 square root 2. So therefore, U dot V is equals to 2. Norm of U, norm of V is equals to 1 times 2 equals 2. So they are equal. So we just show you in this very simple example that, hey, if U and V are pointing to the same direction, and here the word same direction, because here opposite direction is still the same direction, and the reason is because there is this absolute sign here of U dot V showing you that opposite direction is taken care of. Okay, so this is the example we are talking about. All right, and then maybe I have another 5 minutes and I will do triangle inequality. The triangle inequality goes like this. U plus V is less than U. So here he's saying that if I add two vectors up and I take the length is always less than or equal to individual length. So of course you guys know what we're talking about. It is that if I travel along here called U, and I travel along here called V, and here is U plus V, and the length of this guy is always less than the length of the sum of these two guys, right? Because you know that we're bending the endpoint nearer to the origin. So it is less than or less than in this example. When is it equal? Very simple. This is U, and then we travel again. This is V, and then this whole point is U plus V. So when they are in the same direction, then it'll be equality. So equality comes when U and V are in the same direction. In here, it must be the same, the opposite direction. Then, of course, U plus V becomes shorter and shorter. Okay, so this is the triangle inequality. Now, so if you actually look at the lecture notes, we have gone all the way to now from 6.1.1 until 6.1.4 in this about 45 minutes of lectures where we cover. Okay, so you should be able to do part of tutorial one, this tutorial now, and then on Friday, when we have 2 hours, we will finish all of this very quickly. Okay, now uh, before I end, I'm here to answer any questions. And Song Jian asks, inner product is basically dot product. Okay, dot product is a very special case of the inner product. The inner product is the generalization of the dot product. Okay, let me, and in fact, uh, so inner product versus dot product. So the dot product is a specific case in only the Euclidean real. So you realize that dot product is only operating when the vectors are real. Okay, inner product, more abstract vector space, including functions. That means the vectors can also be functions. The vectors, yeah. So that's okay. CA2, is it hard or not? CA2 is generally as hard as CA1. Okay. All right. So I'm going to spend another 2 minutes to answer any questions you all have. Any is yeah, am I going too fast? Maybe some of you all can tell me. All right. So if there's none, okay, please remember, go to watch the videos. Uh, please watch the videos in orthogonality. You'll realize that I break it into different pages. So those that you know, you don't need to watch. And because I break it into very small parts, like 5 minutes and 10 minutes, you just watch what you like. And honestly, you should just download everything and then watch it at your leisure rather than getting it through YouTube, which will get you see a lot of advertisement. And I get no money out of this, so don't worry, you please download. Okay, I have some questions. How is the second one a triangle? It's just a line. Yeah. So when it collapses, then it's just a line. You're right. And because it's just a line, we're talking about triangle inequality here, right? So then the distance between A plus B is the same as the distance of A plus the distance of B. Okay. Any other questions, guys? Right. Now, because this is the first time I'm using Teams to record, I'm going to check, what do you call that? I'm going to check whether the recording works or not, and I'll try to then upload it somewhere for you guys. YouTube channel. How do we prove the Cauchy-Schwarz inequality? Oh, you don't want to go there. Okay. Can send us the link again. The link? The link of the YouTube channel? Okay. Okay, I'll send it here. Linear Algebra 1884. I have no idea why is there. Okay, there's the link. Yep. What chapter tested for CA2? All right, CA2. Okay, CA2 here. Until chapter 6, 7, 8A and 8. And 8 is including only part of it. Now, if you miss this, then all of 8. Okay, so you don't want to go there. So, chapter 9 is is not tested. So every one of you all I know will give it up. And chapter 9 is SVD, singular value decomposition. Any other questions, guys? Okay. When and how we can find out about our quiz one result? Please send an email to Professor Dipu. thanks for the lesson. No, thank you all for attending. How many guys are here anyway? Let me check. No idea how many of you are here. 217. Yay, cool. Okay, 216 now. Someone left. But out of 700 something, so that's a bit shocking. So ask your friends to attend, and it's actually nice if we have some interaction. But yeah, I know it's hard. Okay, now with that, I'm done. So I'll see you guys again on Friday at 8:30. Okay, right. Thank you very much. Goodbye.